Welcome back, everyone. Today we're going to be solving a question from Griffiths, the 5th edition. And in the question, it basically asks us to check that equation 2.29, which is this function over here, satisfies Poisson's equation. And we do this by applying the Laplacian, which is this function over here, and equation 1.02, which I've written out over here. So key thing to note before we start, the Laplacian as we defined it is a function of x, y, and z, which means that it is a function over this vector r. It is not a function over x prime, y prime, or z prime. So keep that in the back of your head. It'll become important later. So we begin by just applying the Laplacian operator to both sides. Now, key thing to note is that 1 over 4 pi epsilon naught is a constant, so we can bring the Laplacian operator inside of that without any issues. Now, similarly, each of these integrals is over x, y, and z, which means, the integrals are not over x, y, and z. The integrals are over d tau prime. And because these integrals are over d tau prime and not x, y, and z, as I incorrectly said earlier, that means that we can bring this Laplacian operator inside the integral. So when we do that, we just drag it in. Okay, now notice that r prime is different to what the Laplacian operator is defined over. The Laplacian operator is defined over x, y, and z. So r, not r prime. So we can also bring it inside of rho of r prime because they do not depend on one another. So just writing that out now, we get 1 over 4 pi epsilon naught Okay, great. So what we have here is basically exactly what we need to apply equation 1.102, which is great because that's exactly what the question asks us to do. So we are going to apply this identity and keep going from there. Okay, great. Now we want to actually compute what this integral is. But to do that, we have to simplify just a little. So let's just get rid of terms that we know we can get rid of. 4 pi's cancel out. Let's bring this minus outside. It's easier to keep track of constants when they're at the front. And we know that this curly r is actually just this, as Griffiths explains. So we can write it out here. So that's great. We're almost done. We just have to apply this delta function, and then we should get the answer we want. So that's great. The goal basically is to use equation 1.92 from the textbook. So in that, they'll basically go from minus infinity to infinity of f of x delta x minus a dx, and that's equal to f of a. This is kind of what we want to use. The only problem here is that in this way of writing, our x would be r prime, and our x here again is r prime, but they're in the wrong place. We kind of need r and r prime to be swapped, so we have to do some delta function manipulating to make that exactly how we need it to be. So let's just write this out as a quick aside. So this really is a three-dimensional delta function over x, y, and z. And luckily for us, we can just subtract, take minus 1 out of every delta function. And that's great. So now we almost have it in the form that we want. To get this minus 1 outside of the delta function, we have to apply equation 1.94. Essentially what it means is that we just bring the absolute value of minus 1 outside each of these delta functions. Do the same for y, and also the same for z. Okay, so at the end of all of this, we actually find that the delta functions are really the same. This is just equal to 1. Therefore, this is equal to this. Great. So if we move on and apply that to this equation, we get that the Poisson v of r is equal to minus 1 over epsilon naught triple integral for r prime Okay, so we can now apply this function without any issue, and that is exactly what we are going to do. And when we do that, we find that this is actually equal to minus 1 over epsilon naught rho of r. The integral is now gone, which gives us the actual final answer that we're looking for, which is that the Laplacian over this potential is equal to just the negative density divided by the permittivity of free space. Great, so that's it. I think the one thing that you should note is that throughout all of my notation, I have dropped the vector notation logo. And I can do this because I have done this a lot before with the vector notations, and this is not being marked. But if you are submitting this for homework anywhere, you should include the vector notation and also where all of these equations come from. Great, thank you very much.